Okay, I guess it would be last time, but it was a video. We started going through normal and tangential coordinates. Yeah, that's fine. Which basically is a coordinate system that we define being attached to the particle as it's moving. And the key thing is that the tangential coordinate is tangential to the path of motion. We went and derived the normal vector, which is simply normal to that tangential vector. And we found that it was equivalent to the derivative of e hat t over d theta. And then flip the page. Okay. All right, so since this velocity is tangent to the path, we can write it as the following. Since the velocity is tangent to the path, we can write it as being equal to, our velocity vector is equal to some script v, which we'll use to represent the speed or the magnitude of that velocity, times e hat t. So it's some magnitude in the e hat t direction. So in order to obtain our acceleration, we're going to differentiate that velocity with respect to time. We're going to have to use a product rule here because both the speed, v, script v, and the e hat t direction, both of these are functions of time. And this will also be something we have to do when we deal with radial and transverse components. You'll have to use product rule there as well. Okay, so our acceleration vector A is going to be equal to d v, the vector velocity dt. And this is going to be equal to, doing a product rule, we'll get d script v dt. That's going to be in the e hat t direction plus script v in the d e hat t dt direction. So what is this d e hat t dt vector? How do we compute that? Are any ideas on how we would do that? Why don't you take a moment and think about it, let's say like 30 seconds, and then I'll tell you when, and then you can discuss with your neighbor and see if you can come up with an idea. All right, take a moment, take like another 30 seconds and just talk with your neighbor and think about it. Okay, anybody have any ideas? Yeah.
You could multiply the e hat normal times how theta changes time.
Multiply e hat theta times. So what are we multiplying specifically?
D e tangential d theta times d theta dt.
D theta dt.
Okay.
Okay.
D e tangential dt. If you know theta is a function of time.
So you want to use chain rule, is what you're saying?
Yeah.
Okay.
Yeah.
Let's see where that goes. So you're saying that we take d e hat t over dt, and you're saying we're going to multiply this. Tell me what you want to multiply, or how you want to expand this.
I would say that's equal to d e tangential d theta.
All right.
Times d theta dt.
And what's that then equal to? Somebody else, what is that equal to? Oh, sorry. Yeah.
The E normal times d theta over dt.
Exactly. So this is d theta dt acting in the e hat and n direction. Okay, so well, we don't know what d theta dt is, and so now we have to deal with that term. We're going to start by looking at the arc length of a circle. The arc length of a circle is given as s is equal to, well, the radius of the circle times the change in angle, or the angle theta. From calculus, you can show that d theta ds, this is equal to 1 over rho, and rho here is what's known as the radius of curvature of the path. So given that, we can then do another chain rule and expand this d theta dt, which we'll write as d theta dt is equal to d theta ds times ds dt. And this is going to be equal to, first, 1 over rho times ds dt. And then, of course, ds dt is equal to the speed, or that script v, such that we find that our d hat t over dt, that is equal to the script v over rho in the e hat n direction. Okay. Such that the acceleration is going to be equal to, or a will be equal to d script v over dt e hat t plus, one second here. Yeah, okay. Script v squared over rho e hat n. And we're going to switch to using dots for time derivatives. So we'll have here the script v dot times e hat t plus v squared over rho e hat n. And that is the acceleration of the particle in normal and tangential coordinates. Okay. And so just as a reminder, the velocity was equal to the script v e hat t. What is the position of the particle in this coordinate system? I'm going to look to my left side for this one. All right, let's do another think, pair, share. Take 30 seconds, think to yourself, and I'll tell you when, and then discuss with your neighbors what the position of the particle is for this coordinate system. All right, discuss with your neighbors. Okay, does anybody have an answer for what the position of a particle is in this coordinate system? We'll start with the left, and if nobody, my left, and if nobody has an answer, then we'll sweep down. And if nobody has an answer, then I'll start calling on people. Okay, what's your name? Naveed? Okay. ds over dt. But we said that ds over dt, if I get my little laser, is equivalent to our velocity. So then the position would be, or the speed, sorry. So the position would be the speed, but what direction? Because the position is a vector that has magnitude and a direction, or directions. Okay, what about over here? Somebody. Yeah.
Read the magnitude as on the direction 1 over en.
1 over en. Interesting. How do you divide by a vector?
They take the perpendicular of that.
Perfect. So in the tangential direction. It's a good guess. However, where is the origin? Or where is the coordinate system fixed? What's the starting point, though? So if we go back, sorry, go ahead.
When t equals 0?
When t equals 0, sure, but what if I say the particle starts moving at t equals 5? So if we go back to the very beginning, we defined this coordinate system as being attached to the particle. In this case, at position P or at position P prime. So the coordinate system is attached to the particle and it moves with the particle. And so the question that I asked of what is the position is not even a valid question. It doesn't make sense to ask or even answer that question because the particle doesn't have a position in this coordinate system because it's entirely defined by its velocity and the direction of that tangential component or the curvature of that motion, the curve that it's following. So there is no position vector in this coordinate system, which is something that's kind of weird in my opinion, but it's due to the way we define this, which is the fact that it's based on the velocity vector, or really the curve that this particle is moving. All right, any questions about that? Yeah?
So for this coordinate system, we're not really concerned with the position, we're just concerned with the angle.
We are concerned with the velocity as well as the acceleration of the particle as it's moving around a curve. And I have some examples that I'll talk about in a moment where this is applied. But generally, we're thinking about how is an object moving around a fixed curve. Such as, for example, well, on Thursday or Wednesday, we're going to do a worksheet where we study a train going around a curve. And we're going to design an optimal track in order to minimize the amount of acceleration the body or the passengers experience.
So what you're saying is there's no way to get an XY position from
What I'm saying, yeah, exactly. I'm saying that doesn't make sense. It doesn't make sense to ask that question given the way we've defined this. The particle is always at the origin of the coordinate system. So it's, if you really wanted to, its position is 0, 0, always. And so if you want to ask what is its position now versus an hour later, it's 0, 0. So it doesn't really make any sense to talk about that. Or at least you don't gain any useful information from that.
Why is this different than like the car problem where we had a coordinate system attached to the car but still we draw position vectors there?
Yeah, the key thing here is that in this case, so in that car, you're talking about the example problem, right? So in that case, this car is following like a projectile type motion. It was exposed to a gravitational field and an acceleration, and it was moving according to that law. In this case, you are prescribing the motion or prescribing the curve that it follows rather than it being governed by gravity. So you can think of like a roller coaster. You know, it's stuck on the tracks, and it is only following those tracks. It's not going to, do anything else. It's not going to go anywhere else now. That doesn't mean it will go up on a loop. It might go up and then come back down or something, but it's forced to move along that path. That's where this comes into play. Yeah.
Well, then, could there be a position where is it along the curve?
You could use that. In that context, you need to use a different coordinate system. So that's a case where you want to switch to like polar or Cartesian, and then you define a fixed origin, and then you would be able to describe where it is, as a position, a function of time. In tangential and normal coordinates, because it's fixed to the body or the particle itself, it does not make sense to describe a position. Okay.
If our position is never changing as a function of time in this reference frame,
Yeah.
how can we say that we have a velocity in this reference frame?
Because the reference frame is moving itself. And so because of that, because it's attached to the particle, the reference frame itself is moving at the same speed and velocity as the particle. That's why. And so we've based our entire coordinate system based on the velocity. And that being said, you could relate this to an inertial reference frame with like Cartesian coordinates, and then you would be able to describe a position vector, and then you'd be able to find a velocity of the particle based on that as well. Okay. Any other questions? Okay. We've got a couple of points to discuss, and then we're going to do an example, and then we'll switch and do radial and transverse coordinates. Okay, so if the particle is traveling in a straight line, then the radius of curvature is infinite, and the normal component of the acceleration is going to be 0. And in this case, you just go back to your standard rectilinear motion where your acceleration is in one direction and it's the derivative of your velocity. And so the acceleration is going to only be 0 when both of these components are 0, meaning that even if you have a constant speed, the acceleration does not necessarily have to be 0 unless it's a straight line, or the particle passes through what's called an inflection point. And just as an aside, an inflection point is a point where the sign of curvature changes. I'm just going to write that here. Inflection point, just so we're all aware, is a point where the sign of the curvature changes. Okay, so this radius of curvature is very important, and it's used in the design of many structures. Just some examples are airplane wings, particularly the section and how that curves, car bodies. Both need to be aerodynamic, both airplane wings and car bodies. Also, what are known as cams. These are just levers and mechanisms used to transmit forces. We'll just leave it at that. And like railroad tracks, roller coasters, etc. Any kind of track design is going to be where radius of curvature play a really important role, and where this type of coordinate system will be applicable. Okay. All right, let's take a 30-second break, and then while you do that, you can read this example and think about it. But I'm not going to ask you to share. We'll just take a 30-second break. Okay, so a ball rolls down a parabolic slope defined by y equals 1/20 times x squared. When the ball reaches a position of L equals 10 meters and a height of h equals 5 meters, its speed is equal to 6 meters per second, and it is increasing at a rate of v dot equals 2 meters per second. We are asked to determine the direction of the velocity and the magnitude of the acceleration at this time instant. Okay, so we need to define a coordinate system first for this problem. In this case, Obviously we're in tangential or normal coordinates, so we're going to use those. So we're going to say that our coordinate system will be fixed to the ball with e hat t tangent to the path and we're going to say that the normal vector points towards center of curvature. Okay, and I actually forgot to erase them on the diagram, so normal and tangential coordinates are already drawn there. We can see that the ET direction at the position drawn has an angle of theta with the horizontal. Next thing we're going to do is compute the velocity. Start with that our velocity vector is equal to the script v e hat t. This is equal to 6 e hat t, and of course the velocity, just as a reminder, velocity is always tangent to the path in the direction of motion. It's always tangent to the path in the direction of motion. So here's a question: can the velocity be negative in this coordinate system? Does it make sense for it to ever be negative? Seeing a lot of head shaking now. Yeah, I never actually thought about this. I just thought about it right now, and I agree with you. And the fact is that the whole coordinate system is moving based on the velocity as well. So if the particle, let's say, goes up the slope, and then it reverses directions, then that whole coordinate system is going to flip as well. So it doesn't make sense to have a negative velocity in this coordinate system. It doesn't mean that if you use like Cartesian or something, you wouldn't have a negative velocity. It depends on your coordinate system that you choose. Okay. All right, so we are given the slope of this, we're given the equation y equals 1 over 20x squared that describes the curve. We're going to use this to find our angle theta, and then from there we'll be able to determine the direction that is acting with respect to that horizontal. So the question when it says to determine the direction of the velocity, what we're really trying to find here is theta, that angle theta with respect to the horizontal. So let's add a little note here. We're trying to find the direction here with respect to horizontal. In other words, theta. Okay, so from calculus you can show that the tangent of theta is equal to dy dx evaluated at x equals L here. Let me just check here. So that is the position that it has, or that is the position on the curve that we're interested in. So we're going to go ahead and compute that derivative. Y is equal to 1 over 20 x squared. Therefore, dy dx, we'll leave the evaluated x equals L. It's going to be equal to, we'll bring down the 2, we'll get 2 over 20, that's 1 over 10, and then times x, so we'll get x over 10, evaluated x equals L. Therefore, we get L over 10 is the value of tangent theta. We know that L is equal to 10 meters, so therefore the tangent of theta is equal to 10 over 10, which is ultra convenient, which is equal to 1, and then therefore theta must be equal to the inverse tangent of 1, which is then equal to pi over 4 radians, or if you want, 45 degrees. Generally in this class you're going to want to use radians and not degrees, generally. That means that if you have a calculator, you're going to want to check that you're using radians on your calculator and not degrees, because if you're not, you will get the wrong answer. And that would be, very unfortunate on something like an exam. Okay, so that is what our theta is equal to, pi over 4 radians. Okay. I'll leave that up there. We're now going to move on and look at our acceleration. The acceleration vector was equal to speed dot e hat t plus v squared over rho e hat n. We're going to need to find rho here, and it's not a very pretty formula, but it is 1 plus the quantity 1 plus dy over dx, that quantity squared, all of that raised to the 3/2 divided by absolute value of d squared y dx squared, so that's the second derivative of y with respect to x, all of that evaluated at x equals L. Whew. Okay, so we're going to need the second derivative of y, and that, if we go back up here, we found that first derivative was equal to x over 10, so the second derivative is just going to be 1 over 10. Actually, was there any questions about what we did for the velocity to find theta? So this you stop here. This tells you where E hat t is at the starting point. Let me check my question. Oh, I'm sorry. Yeah, that is the position. If we come back up here, so I've labeled an origin down here. We're asking when L is equal to this point, what is the direction of E hat t? And we define that with respect to the horizontal. I mean, a snarky answer would be that it's in the direction of the velocity, which would not be incorrect, but doesn't tell us anything new. Any other questions? Yes.
Where did you get that equation from?
Yeah, I pulled it from a calculus textbook. Yeah, and yeah, so I mean that's basically where it comes from. We're not going to derive that. I won't expect you to memorize some of that. On exams, you'll be allowed to use like a page of notes from back, and that's something you could write down. Probably be something I would give you on like an exam, in all honesty. Not the formula, but like I tell you what rho is. Now rho might be a function, but I would tell you what it is. At least I think I would. Don't hold me to that. But the goal is for the exams to be easier than the homeworks, but still cover everything. So, okay. Any other questions? Okay. We are going to move on to our acceleration then. We computed the second derivative of y. And we're going to go ahead and we're going to plug that in and find what rho is, evaluate at what x equals L. So rho is equal to 1 plus the quantity 1 over 10 x, oops, that's the quantity squared, all of that to the 3/2 over the absolute value of 1 over 10, evaluated at x equals L, which is 10 meters. And if you go ahead and you do this calculation, you'll find that the rho is equal to 28.28 meters. And now that we know rho, we also know what v is, and we were given the acceleration, or we were given what v dot is. So we were given what v dot is. We can now just go ahead and compute our acceleration at this point. So a is equal to 2 e hat t plus 1 point. Hold on, I skipped a step. So we'll say v dot e hat t plus v squared over rho e hat n, and here we're going to start plugging things in. So we will get 2 e hat t plus 36 over 28.28. So that v was equal to 6. I believe we said right. Yep, it's equal to 6. 6 squared is 36. And we left out the e hat n direction. E hat n, all of that's meters per second squared. So then the acceleration is going to be equal to 2 e hat t plus 1.273 e hat n meters per second squared. And that is our acceleration. Okay, any questions on this so far? Yeah.
Is that finding the magnitude? Or do we need to find like a
Oh,
number?
you're right. I did not find the magnitude. Alright, I'm going to need some help. Does anybody have a calculator with them? So, acceleration magnitude is going to be equal to square root of 4. That's going to be 2 squared plus the quantity 1.273 squared. Again, that will also be in meters per second squared. And if somebody could calculate that for me, I would be very grateful.
2.37.
2.37 meters per second squared. So the answer here, magnitude of the acceleration vector, is 2.37 meters per second squared. And that's our final answer. We'll go erase that. Good call. Okay, any questions on normal and tangential coordinates before we move on to radial and transverse? Okay. Alright, so now we're going to consider another coordinate system which we call radial and transverse components. This is in like a 2D plane. You could call this polar coordinates. In 3D this becomes cylindrical, where you'll end up with the third direction will be just a rectangular coordinate. So we're going to consider a particle moving along a curve, any curve this time. It doesn't need to be prescribed by us, but just any curve in general. And we're going to define its position vector from the origin to, well, its position P. We'll call this R. That's our position vector. And we're going to define 2 unit vectors. One is going to be pointing from the origin to the current position, and the other one is just going to be normal to that. based on the right-hand rule. So first one points towards the current position, and we'll call that E hat r. So that's our radial coordinates. And then normal to that will be E hat t, and that is our transverse coordinate. Or sorry, we'll actually use E hat theta here to prevent confusion with tangential coordinates. So that's our transverse coordinate. And here, let me draw a straight line here. This angle here is theta. Okay, so E hat r is a unit vector that defines the radial direction. E hat theta is a unit vector that defines the transverse direction. E hat r is specifically defined to point from the origin to the position of the particle, and it follows the position of the particle as well. Meaning that this coordinate system, it's fixed at the origin, but it rotates as the particle moves. Okay, so by definition, E hat r dotted with E hat theta is equal to, what should that be equal to? It should be equal to 0 because they're normal to each other. So the dot product, by definition, has to be 0. Alright, so a way to think about this is E hat r is the direction that the particle moves if we fix theta, and then E hat theta is the direction that P can move if the current position r, not the position vector, but the distance from the origin to the particle along the E hat r direction, if r is fixed, in other words. Something I forgot to write here is that the position vector in this coordinate system r of t, this is defined as some scalar r of t in the E hat r direction. So in this case, even though the coordinate system is still moving, we do have a position vector in this case, unlike the previous case. And so this r that I have written down here, r of t here, if we fix that coordinate, then the particle can move in the E hat theta direction, which means still that theta will grow. Okay, so similar to tangential and normal coordinates, we can show that d E hat r over d theta is equal to E hat theta, and d E hat theta is equal to, well, actually in this case it's going to be negative, it's equal to minus E hat r. This is something we were not going to go through and prove. Typically at like a graduate level, this is something you would go and prove, do a proof for. In this class, you're just going to take these at face value, and if you're really concerned, you can come see me and we'll go through it. Okay, so we get our position vector. We're now going to go and compute a velocity vector, and then we're going to go and compute the acceleration vector. And then we'll have to use these conditions in order to find those vectors. So we're going to start with our position vector. We said that r was equal to, I'm going to drop the function notation. We're going to say r is equal to r E hat r. And then we're going to compute d r vector over dt. And this will be equal to, well, we're going to use a product rule here, dr dt in the E hat r direction, plus r d E hat r over dt, which we will write as r dot E hat r plus r d E hat r dt. Is everybody comfortable with this dot notation? Did I go over that in the lecture videos previously? Okay, great. Fantastic. We're going to use dots a lot because it's way more convenient than writing full derivatives out. Okay, so just like we did in tangential and normal coordinates, we're now going to apply the chain rule. In this case, we're going to get d E hat r over dt. It's going to be equal to, well, d E hat r over d theta times d theta dt. Yeah, my notes I have d theta dr, but that can't possibly be right. Yeah, it must be dt. Yeah, and that's going to be equal to theta dot. And right above we said that d e hat r over d theta was equal to e hat theta. So this is theta dot in the e theta direction, such that our velocity vector r dot is equal to scalar r dot e hat r plus r theta dot e hat theta, which is equal to, well, we'll use velocity vector v. So in this class we will often use like r dot for velocity vector, and we'll also use v interchangeably. Okay. Any questions so far? Okay. So to find the velocity or the acceleration vector, we are just going to go ahead and take another time derivative. So we're going to differentiate, and we're going to get r vector double dot is equal to, and we're going to need to do here both a product rule twice and chain rule as well eventually, although we'll kind of skip the chain rule stuff. We're going to get r double dot times e hat r plus r dot e hat r dot plus r dot theta dot e hat theta plus r theta double dot e hat theta plus r theta dot e hat theta, and that's also dotted. So we actually did the product rule 3 times here. This quantity here, if you go ahead and you do the chain rule, you'll find that it's equal to r dot theta dot e hat theta. This last term over here, if you go and do the chain rule, you'll find that it's equal to minus r theta dot squared e hat r, such that the acceleration vector r double dot is equal to the quantity r double dot minus r theta dot squared e hat r plus r theta double dot plus 2r dot theta dot e hat theta, and that is our acceleration vector. Actually, we can say that's a. Draw a square. Alright, so that's our acceleration vector here. So to write out a couple terms here, oops, this r dot scalar is equal to the translational velocity, where it's defined as the translational velocity. Then r, the scalar r double dot, this is the translational acceleration. Theta dot, it's defined as the rotational or the angular velocity. Theta double dot is then the rotational or angular acceleration. And the acceleration vector is a combination of all 4 of these. So it is not just a simple combination of translational acceleration and rotational acceleration. It is a combination of all 4 terms. Okay. So this is a case where it really pays off if you start by defining a coordinate system, finding position vectors, then velocity, and then the acceleration. Because when you tend to use coordinates like this, or if you have any kind of rotating system, things become very messy very quickly, and it becomes very hard to just look at a system and determine the acceleration with just looking at it. And so using a very methodical approach will get you the right answer every single time. Okay, any questions on this? Yeah.
So this coordinate system is just applicable, it's kind of like a more expensive version of what we did before with the tangential coordinates.
Yeah, so we're about to talk about how they're not the same in general, but this is a coordinate system that is very useful for rotating systems. That being said, there are rotating systems where this is not useful, actually. We're going to look at an example of a pendulum, and I think we'll look at, I mean, all the examples I have are useful, but if you have what's known as like a double pendulum, so you got one pendulum here, if we were to come and attach another mass to this thing, and now you've got two coordinates to keep track of, this is a case where you would need two sets of what are these, radial and transverse coordinates to track both of these, and then you end up having to just go to a Cartesian coordinate anyway. So it's really when you have a single particle, and that could be a chain of particles that are originally connected somehow, that's where this becomes the most useful. Okay, any other questions? So something like a pendulum, we'll see how this really simplifies that problem dramatically versus using Cartesian, where you end up with two coordinates and you've got to define what's known as a constraint equation in order to relate those two coordinates. When we do with a pendulum, you'll find that there's a single coordinate. Okay. Okay. Any other questions? Okay. Okay, so we'll just take a quick look at a quick mini example just to demonstrate how normal and tangential are not the same as polar coordinates. So we have here a particle moving along some loop. We've defined an origin. We're going to draw a position vector from our particle, or from the origin to the particle. We can just call this R. Let's define first our E hat R direction, and then here's our E hat theta direction. And those are defined based on the position of the particle from the origin to the current position is what E hat R is defined as. At this point, I've put this particle at a very specific point such that the tangential, or the velocity, the particle is actually moving like this. And so the E hat T direction points upwards. And then in this case, the E hat N direction points inwards to the center of that curve. And here you can clearly see that these coordinates are not the same. I mean, they are obviously defined differently, but they will not be the same. Okay. All right. We're going to look at 3 different examples. We likely will not finish them, so we'll finish the examples on Wednesday. We'll try to finish all of the notes on Wednesday, but we'll go through, starting with the pendulum. This is probably the simplest system where radial and transverse coordinates make the most sense. We're just asked to determine its acceleration in polar coordinates, polar or radial and transverse, same thing. So we're going to start off with our coordinate system. I forgot to erase that, so we've attached our coordinate system at the origin, which is at the point where the pendulum connects to the ground. And then we're going to use radial and transverse directions, and then we're going to say that counterclockwise rotation is positive here. So we're going to say origin at the top of the pendulum. We're going to use our radial and transverse directions. And then counterclockwise rotation is positive. And that just comes from our right-hand rule. Okay. Go on to our position vector. R is going to be equal to L E hat R, simply because it is from the origin to its current position, and that is a distance L in the E hat R direction. There's really nothing more to say there. Now I want you to go ahead and compute the velocity vector, and you can work with your neighbor. And if you find the velocity vector, I want you to go and compute the acceleration vector as well. And I'll come walk around and try and give some feedback.
Yeah, that's the other everything else. It just got right. That's already known. Yeah. So you did it because this is x and y. If it's tangent, tangent data is equal to change y over change x. So we can't do that because we're changing the time. Unless we find data Theta changes with something else, and then so we kind of just take the general formula, but then we need to find theta time, which we think is going to depend on gravity. Or it's just theta. You need other, yeah. Okay. Is this what you get for It's just L dot E theta direction. Still working on that accelerated.
So for theta dot, you just leave it as theta dot. You don't know what that is. You don't have enough information to determine that. You guys, one more minute.
I don't know if this is true, but that's true.
All right, I'm going to go ahead and I'm going to solve this, and then I'm going to start the second example, which we'll probably finish in the next class, and then we'll work on the third example next class as well. Okay, so once we have our position vector, we need to find our velocity vector. We're just going to take the time derivative of that. We can also just use the formula that we derived above as well. In this case, the scalar r is equal to L, or the length of the wire from the origin to the pendulum. So we're going to get here, we're going to get L dot E hat r plus, we would get L times E hat r dot, which is equal to theta dot E hat theta. So we'll get L theta dot E hat theta. L is a constant, so its derivative with respect to time is 0. So that goes to 0, such that r dot vector is equal to L theta dot E hat theta. And that is our velocity vector. Like I mentioned, we don't know what we don't know what theta dot is. You need more information and more techniques to be able to solve and find what that is. Moving on to the acceleration vector, we'll just take a time derivative of the velocity. So we're going to get, starting off with L dot theta dot E hat theta plus L theta dot E hat theta plus L theta dot E hat theta dot. Oh, not over the theta, it's over the E hat. So again, L is a constant, so L dot is 0. Let me do that in green. Leaving only the other two terms. E hat theta dot is equal to minus theta dot E hat r. So we're going to end up with minus L theta dot squared E hat r plus L theta double dot E hat theta, such that our acceleration vector r double dot is equal to minus L theta dot squared E hat r plus L theta double dot E hat theta. And that is our acceleration vector. At this point, we don't know, I didn't tell you about a numerical value for L. We don't know what theta double dot is. We don't know what theta dot is, so we're just going to leave them as unknown variables. Okay, so that is the acceleration of a pendulum at any given point in time. Not to say that you know what theta dot or theta double dot are, so you can't really compute what it is, but that is the formula. Are there any questions on that example or what I did there? Okay, in that case we're going to go on to another example. In this case we have a particle moves along a path defined by r equals a times the quantity 1 minus cosine theta, where a is a constant here, and we're asked to determine its velocity and acceleration. In this case, since we are given a function that defines its position with respect to the origin, this is a case where you're going to want to use these polar coordinates or radial and transverse coordinates. So we're given an origin. Again, forgot to erase the coordinate system, so it's there. We'll just say that the origin is at position when theta is equal to 0. We now want to determine the position vector. R is equal to r e hat r, but we are given what r is equal to, and so in this case we'll find that the position vector r is equal to that constant a times the quantity 1 minus the cosine of theta e hat r. So this is a case where that position vector is actually dependent on the angle theta. Meaning that its position does change as a function of time, whereas in the case of the pendulum, the position is constant, though the direction is changing as well. In this example, both the magnitude and the direction of that position vector are changing with time. So we're going to go ahead and we're going to compute the velocity vector. R dot is equal to a dot, and we've got to do product rules here as well. There's 1 minus cosine theta e hat r plus, we'll get a, we're going to take the derivative inside the parentheses, we'll get derivative of cosine is minus sine theta times minus 1 gives us a positive sine of theta, so we get sine theta, and then we're going to do chain rule and take the derivative of theta, so we're going to get out here, I'm going to actually put it in the front, we're going to get a times theta dot sine of theta. And that's still in the e hat r direction, plus a times 1 minus cosine theta e hat r dot. Okay. So this is going to be a times 1 minus cosine theta dot e hat theta, such that the velocity vector r dot is equal to a theta dot. Oh, we said a was a constant, so this whole thing is 0. And then we have that a times theta dot sine theta e hat r plus a theta dot times 1 minus cosine theta e hat theta. That is our velocity vector. Okay, and this term right here, that's our r dot e hat r. This term here is the r theta dot e hat theta term that we saw when we originally derived these. Okay, to find the acceleration, we're going to take another time derivative here. So we're going to just go and compute that. We're going to get r double dot vector is equal to We're not going to take derivatives of a because it's a constant, so we're just going to skip writing those out because there are a lot of other terms to deal with here. So we're going to get a theta double dot sine theta e hat r plus a theta dot squared cosine theta, that comes from the derivative of the sine of theta, still in the e hat r direction, plus a theta dot sine theta e hat r dot, and those three components come just from the e hat r direction. If we had included the a dot terms, we would have had an extra term there, plus a theta dot times theta double dot minus cosine theta e hat theta plus a theta dot squared sine theta e hat theta, and plus a theta dot 1 minus cosine theta e hat theta dot. We go ahead and combine all of these terms. We're going to find that the acceleration vector r double dot is equal to the quantity a theta double dot times the sine of theta plus a theta dot squared cosine theta minus a theta dot squared 1 minus cosine theta, all of that in the e hat r direction, plus a theta double dot 1 minus cosine theta plus 2a theta dot squared sine theta, and all of that is in the e hat theta direction. Okay, one more thing. Actually, let's go ahead and we're going to draw a little box around this because this is our solution. And then one last thing, I just want to point out that this here is r double dot. This here is minus r theta dot squared. This term here is r theta double dot. And this last term is 2r dot theta dot. And then with that, we are done with the class. If you have any questions, since we're out of time, you can ask me right after.